We've already talked about how a derivative tells us about a rate of change for a function, and that the derivative can be used to find the slope of a tangent line at any point on that function. Now, we used a couple of methods to find derivatives. One was by using limits, and then we had some derivative formulas that we've used, which were the power rule and the sum and difference rule. We'll be adding to those rules in just a little bit, but before we do that, let's look at some ways that we can use this idea of a derivative as telling us about a slope of a tangent line. So let's see if we can find the points on the graph of f of x equals negative x cubed plus 6x squared at which the tangent line is horizontal. Now let's think about what we know. We know that the derivative will tell us the slope of a tangent line at any point along a curve. And we know that since we want to find a tangent line that's horizontal, it will be helpful to know that the slope of a horizontal line is 0. So what we need to do is find all the points on this graph where the derivative of f equals 0, because that's where the tangent lines will have slopes of 0. So let's find the derivative of the function. And we want to know where the derivative is equal to 0, so we'll set that derivative equal to 0 and solve for x. We have to do a little algebra, so we'll factor, set the factors equal to 0, and then solve for x in each factor. So what we know is that there are two x-coordinates on this graph where the tangent line to the graph will be horizontal. We'll have a slope of 0. Now we need to find the y-coordinates that go along with each of those x-coordinates. Remember, it's the original function that tells us the relationship between the x and y coordinates of points on the graph. So we need to use the original function to find the y-coordinates to go along with each of our x-coordinates. So when x is 0, our y-coordinate is also 0. So 0, 0 is one place on this graph where we have a horizontal tangent. And when x is 4, we know that our slope of the tangent line is 0. The y-coordinate that goes along with that x-coordinate is 32. So 4, 32 is the other point where we'll have a horizontal tangent line. This is what the graph of the function looks like. Remember, we got two x values where the derivative was equal to 0, which means we had two places on our graph where the tangent line to the graph was horizontal. Now let's try this problem. Alexis enjoys jumping on her backyard trampoline. Her motion can be described by the equation f of x equals negative 16x squared plus 24x, where x represents the seconds passed since the start of her jump, and f of x represents her height in feet above the trampoline at time x. How long does it take her to reach her maximum height? What is her maximum height? And how long does it take her to return to the trampoline after her first jump? Well, this is the equation that describes Alexis's motion. We know that it's a quadratic function because it's a polynomial function. That tells us that the graph of this function would be a parabola. We also know that that parabola would open down because the coefficient of the squared term is negative 16. The vertex then is going to be the highest point on this parabola, so the vertex will give us the maximum value for the function. We know that the maximum height will occur where our derivative is equal to 0, because the slope of the tangent line at that point will equal 0. If we were going to graph the function, we know that x, which represents the time in seconds, would be represented on the horizontal axis, and f of x, which represents the height in feet, would be represented on the vertical axis. Since this is a parabola that opens down, our graph would look something like this. If we want to know the height that she reached at her maximum point, we're looking for the vertex, and in particular we're looking for the y-coordinate of the vertex. If we want to know the time that that occurred, we're looking for the x-coordinate of the vertex. So let's take the derivative of the function. We know that at the vertex, that derivative will be equal to 0 because the slope of the tangent line is equal to 0 at the vertex. And if we solve that equation for x, we get a value for x of 3/4. Now remember, x represents time. So we know that that maximum height will occur after 3/4 of a second. To find the maximum height, we want to know how high she is at 3/4 of a second. So we want to know f of 3/4. F of 3/4 we find by substituting 3/4 into our function, and we'll find that her maximum height is 9 feet. So the vertex of this graph is at 3/4, 9, where 3/4 means 3/4 of a second after she started to jump, and 9 means 9 feet in height. Now the second thing that we can find at this point is how long it takes her to return to the trampoline after her first jump. This is the point on the graph we're interested in. It's the point where our height is 0. Notice we're not going to be using a derivative to find this because we're looking for a point on the function where the height, the value of f of x, is equal to 0. If we solve this equation by factoring and setting the factors equal to 0, we get two values for x, which might seem a little strange at first, but it really makes sense if you look at the graph. The first value for x equals 0, is this point on the graph, 0, 0. That means when no time has passed, she has no height. She's standing on the trampoline. The other point on the graph is 3/2, 0. That means after 3/2 seconds, or 1.5 seconds, she'll be back down to 0 feet above the trampoline. So there are actually two places on this graph where she's back down at ground level, so to speak, the level of the trampoline. The one that answers the question is the second of these points. She'll be back to the trampoline after 1.5 seconds. Because this is a parabola, there is one other way we could have found this answer, and that is by recognizing that a parabola is symmetric, and we already know where the vertex of this parabola is. So, since it's symmetric, and we know that the vertex, the halfway point in her jump, happens after 3/4 of a second, we also know that she's going to land back on the trampoline at twice that 3/4 of a second. So, that's 3/2 of a second, which is still 1.5 seconds. Now, before we leave this problem, let's think again about what's really going on. At this first point, 0, 0, no time has passed, and she has no height. She is standing on the trampoline. At this point, 3/4 of a second has passed, and she's 9 feet above the trampoline. That's her maximum height. It's the point that is the vertex of the parabola, and it's the point where the derivative was equal to 0. We had a horizontal tangent there. And at this point, our time is 3/2, so it's 1.5 seconds after she initially jumped from the trampoline, and her height off of the trampoline is 0 feet, which means she has landed back on the trampoline. Now we've got several differentiation techniques, several rules that we can use to find derivatives. We're going to add a few more now. One thing we know how to use is the power rule. So to find a derivative of x to the 8th, we know that we just bring the 8 down front times the x to 1 less power, so 8x to the 7th power. Finding this derivative is related to finding the derivative of x to the 8th because we still have something to the 8th power. But that something, that base, is more than just an x. It's a function in and of itself, 5x to the 3rd plus 2x squared. So in order to find this derivative, we're going to use what's called the extended power rule. Now this is what the extended power rule looks like, and it looks pretty complicated when you write it this way, but here's what it's saying. If we want to find the derivative of some function to a power, then we're still going to bring that power down in front, that's the k, times that base to 1 less power, but then we have to take that times the derivative of the base. So how does that work with something like this? Well, the first part of our extended power rule says we're going to bring the power down front, so there's our 8, times that same base to 1 less power, but now we have to take that times the derivative of the base. So the derivative of 5x to the 3rd is 15x squared, and the derivative of 2x squared is 4x. Now the extended power rule even works with this, because we have a base that's more than just an x. It's 1 plus x to the 3rd raised to a power. So for our extended power rule, we'll simply bring the 1/2 down front times our same base, 1 plus x to the 3rd, to 1 less power. So 1/2 minus 1 is negative 1/2, but now times the derivative of the base. The derivative of 1 plus x to the 3rd is 3x squared. Remember, the derivative of 1 is 0. Let's see how we would do something like this. If f of x equals 2x plus 5 times 3x minus 11, find f prime of x. Find the first derivative. Well, I don't see any powers, so this is not going to be a power rule. Let's try doing a little bit of algebra on this to rewrite it before we do the derivative. Because I notice this is just a binomial times a binomial. So you remember using the FOIL method to expand a binomial times a binomial. So if we multiply 2x plus 5 times 3x minus 11 and combine our like terms, we get 6x squared minus 7x minus 55, which is still our original function. We have not done a derivative yet. But now we can take the derivative of that function. Derivative of 6x squared is 12x. The derivative of 7x, or minus 7x, is minus 7. And the derivative of minus 55 is 0. So our derivative is 12x minus 7. So sometimes you'll see that doing a little bit of algebra on your function before you do the derivative may make the derivative pretty easy to do. But that's not the only way to do this problem. So let's look at another rule that can help us do that derivative, and it's called the product rule. It says if we have a function that's made up of two functions multiplied together, in this case we're calling them g of x and h of x, then the derivative of our function is equal to the first function times the derivative of the second plus the derivative of the first times the second. So let's go back to this problem. We've already done the derivative once by expanding the product first and then doing the derivative. Let's do the derivative of this function using the product rule. Now we can do that because it is a product. The product rule says that we need to have two functions that are multiplied together, and we have that. The 2x plus 5 is one function and the 3x minus 11 is another. So as we do this, you can think of the 2x plus 5 as the g of x and the 3x minus 11 as the h of x. So here we go. First we need our first factor, which is 2x plus 5, that's g of x, times h prime of x, times the derivative of the second factor. So the derivative of 3x minus 11 is 3, plus the derivative of our first factor. So the derivative of 2x plus 5 is 2, times our second factor, times our 3x minus 11. Now if we do a little bit of algebra on that, remember we've done the derivative at this point. We just want to do the algebra to rewrite this. So 2x plus 5 times 3 is 6x plus 15, and 2 times 3x minus 11 is 6x minus 22. So what you're going to see is that sometimes we have more than one way that we can do a derivative, but we'll always get the same derivative no matter what method we choose, even though we may have to do some simplifying to make those derivatives look the same. So let's try this. Our function looks a little more complicated, but you'll notice that it still is a product of two other functions. So in order to use the product rule, we're going to take the first of those factors, 2x cubed plus 9, times the derivative of the second factor, plus the derivative of the first factor. So the derivative of 2x to the third plus 9 is 6x squared, times the second factor. Now at this point, we've done the derivative. Anything we do after this is simply algebra to rewrite the derivative. So let's do that and combine like terms, and we get our derivative. Wow, 50x to the fourth minus 24x to the third plus 24x squared plus 90x minus 27. Now you may be wondering, how far do I have to go with this? And it's going to depend upon what we're doing with it. At this point, we're just practicing differentiation. So quite often what you'll see written is something like, find the derivative, do not simplify. In that case, we would stop at that first step you see, our first line that says f prime of x equals. However, if the instructions say to simplify, then you're going to want to go ahead and do the algebra after that to get down to the last line that you see, which is our final simplified version of our derivative. Now there's one more rule that we're going to use, and that's called the quotient rule. This says if you have a function that consists of a fraction, a quotient, it's a numerator divided by a denominator. So n of x means numerator and d of x means denominator. Then the derivative of the function can be found by creating a fraction, and the numerator of that will be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, and all of that is divided by the square of the denominator. Now let's see how that works on this. F of x is this fraction, this quotient, and we want to find the derivative of it. So, according to the quotient rule, we're going to have to identify what our denominator and what our numerator are. The x squared minus 3x is our numerator, so that is what is called n of x in our quotient rule formula. And the x minus 1 is our denominator, so that is d of x. So here we go. Here's our derivative. First we need our denominator, d of x, times the derivative of the numerator. Derivative of x squared minus 3x is 2x minus 3, minus our numerator, x squared minus 3x, times the derivative of the denominator, which is just 1. And that we divide by the denominator squared. Now this is our derivative. Anything we do after this is simply algebra to rewrite the derivative. So if we multiply the x minus 1 times the 2x minus 3, and then we multiply the 1 times the x squared minus 3x and subtract that, we have this. And if we combine like terms, we finally get to this, which is our simplified form of our fraction. Let's see if we can take this derivative. Now it looks like a fraction, so we ought to be able to use the quotient rule. So let's see how that would look. We need the denominator times the derivative of the numerator. So the derivative of 6, the derivative of a constant, is 0, minus the numerator, which is 6, times the derivative of the denominator over the denominator squared. So we've done our derivative. Anything we do after this is simplification. So I notice we have an x squared plus 4x minus 7 times 0. That's just equal to 0. So our final simplified fraction is negative 12x minus 24 over x squared plus 4x minus 7 squared. We could use the extended power rule if we rewrite the original function. We'd have to rewrite it like this. We'd have to take that x squared plus 4x minus 7, bring it up to the numerator, which would give it a negative first power. Remember, that is not a derivative. We're just rewriting the original function. But now we could use our extended power rule and take the derivative of that version of our function, which would be 6 times, now bring that power down, times negative 1, times our base to 1 less power, times the derivative of the base. If we simplify, we'll see that we get exactly the same thing we got when we used the quotient rule on this problem. As you can see, we sometimes have a choice of methods to use to differentiate a function, but we should always get the same answer no matter what method we decided to use. One last problem, and this one's going to look a little bit involved, but let's see if we can figure out how to approach it. First, we have to decide what the appropriate derivative rule is going to be. And what you probably notice first of all is that we do have a product, because we have two things that are being multiplied together. So we can certainly use the product rule. But each of those factors that are multiplied have a power, and their bases are more than just x's. So that means we'll also be using the extended power rule as we do this derivative. So let's keep in mind what the product rule is. In order to take the derivative of this function, we need the first factor times the derivative of the second plus the derivative of the first factor times the second factor. Okay, so here we go. We need our first factor times the derivative of our second factor, which is 6, times our base to 1 less power times the derivative of our base, plus the derivative of the first factor, which is 2 times the base to 1 less power times the derivative of the base times our second factor. Now that's our derivative. It is not simplified, and we certainly could do some simplification by factoring out some common factors. But at this point, I'm going to just leave it like this. We'll work on simplifying things like this at a later time. So we've got some new rules that we can use for differentiation, and we've seen some applications for those rules. So we'll get a chance to practice all of those in class.